Welcome to Earth Science Lecture. This is Professor Diana L. Pomeroy, and this week we'll learn about weather and climate. Weather is the daily and weekly change to the Earth's atmospheric chemistry, temperature, and pressure that results in phenomena like clouds and storms on Earth's surface. Climate is the average of weather patterns over a long period of time, be that decades, millennia, or millions of years. The left diagram is a weather forecast for 1 week in New York, with temperatures listed in degrees Fahrenheit. And the right diagram is a climate model graph for the entire Phanerozoic eon of time, which is approximately 540 million years of weather patterns that are inferred from the fossil record and from ice cores collected at the poles. The sun warms the Earth's surface and provides energy to it through solar radiation. This heat energy gets absorbed by the ocean, and the first phase of the water cycle, evaporation, begins. The surface waters of the ocean become water vapor, rising through the atmosphere and condensing into structures that we call clouds. As clouds gain density due to water droplets that build up within them, and due to temperature and pressure conditions in the atmosphere, the clouds will eventually break, leading to precipitation, or rainfall or snowfall. This water has several fates. In the Rivers and Groundwater lecture on my YouTube channel, you'll learn more about runoff. And in the Glaciers, Ice Ages, and Climate Change lecture on YouTube, you'll learn more about how glaciers form and affect phases of global warming and global cooling on Earth's surface. Eventually, the majority of surface water flowing on Earth ends up in the oceans, starting the water cycle all over again. The Earth's atmosphere is divided into several layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The troposphere is the layer where weather and climate phenomena occur, which is between 0 and 12 kilometers above the Earth's surface. For comparison, note that the peak of Mount Everest is about 8 kilometers above Earth. Between each layer of the atmosphere is a pause, a point in which the temperature and pressure of the layers above and below that pause level out. The tropopause is where many commercial airliners fly. This is termed above the weather. Note that the temperature, which is presented in the graph on the left in degrees Kelvin, and the pressure presented in the graph on the right in torr, decrease dramatically as you move from the surface of the Earth through each layer of the atmosphere. There are subtle differences in temperature and pressure in air masses that collect closer to Earth's surface, and instability in air masses in the troposphere is what leads to changes in weather patterns over time. The instability in air masses in the troposphere is due to multiple factors: the chemistry of the Earth's atmosphere and its retention of heat, and the temperature and pressure variability of the air masses that are due to wind patterns and atmospheric circulation conditions. The chemical composition of the troposphere is approximately 79% nitrogen and nearly 21% oxygen. The remaining 1% of the troposphere is comprised of substances known collectively as greenhouse gases. These include water vapor, carbon dioxide, methane, and ozone gas. Changes in the amounts of these gases, greenhouse gases, in the troposphere, especially carbon dioxide in comparison to oxygen levels, can lead to weather pattern changes over time that can result in a climactic shift. The troposphere has variation in air mass movement due to the rotation of the Earth on its axis. The rotation of Earth creates disturbances in air mass energy. This creates waveforms in the troposphere. These atmospheric waves include two major types, which are gravity waves and planetary waves. Gravity waves, which are shown on the left, are compressional waves. These generate turbulence in the upper atmosphere, especially where mountain passes. Planetary waves, which are shown in the diagrams on the right, are developed as the Earth rotates on its axis. These waves move along each major latitude, and they generate weather patterns in the upper atmosphere. The jet streams are constantly flowing air masses. Think of them as rivers of air that move at speeds of hundreds of miles an hour above the Earth's surface. There are two jet streams, one near the poles and the other near the equator, in each of Earth's hemispheres. Rossby waves are a type of planetary wave that move the jet streams farther south or north than usual. This in turn affects air mass temperatures and pressures in the troposphere and can change weather conditions on Earth's surface. Rossby waves can generate hurricanes or cyclones at lower latitudes due to this disturbance as well. So in this image, we've got a globe of the Earth, and we have the polar jet stream that is flowing in red in the uppermost portion of North America. Weather fronts occur when evaporation of the ocean is coupled with atmospheric pressure changes in the troposphere. Low pressure systems are caused by warm air masses that override cold air masses. That is termed a warm front. A series of low-density clouds are developed in the upper reaches of the troposphere when a warm front is passing over an area. These are termed cirrus and stratus clouds. High-pressure systems, on the other hand, are caused by cold air masses that overtake warm air masses. This is termed a cold front. A series of high-density clouds form close to Earth's surface, generating static discharge within them as they build. The static discharge is known as lightning. This is then followed by the sound, thunder, as lightning strikes the Earth's surface. The clouds that develop here are known as cumulonimbus clouds, and they converge over an area during a cold front event. Severe storms are often associated with cold fronts, and sometimes cold and warm fronts can converge, creating really stormy weather for days or even weeks at a time. Weather fronts can be mapped out, as seen in this NOAA image of the United States. Warm fronts are indicated by a red L for low pressure system, and a series of red half circles on a contour line. Cold fronts are indicated by a blue H for a high pressure system, and a series of triangles on a contour line. When these fronts converge, a purple line is generated. The rotation of the Earth on its axis, the degree of axial tilt, and its placement along the plane of the ecliptic, or its path of orbit around the Sun, cause fronts and winds to move across the Earth's surface as well as the seasons to occur. This diagram shows the dates of the solstices and equinoxes for North America. The differential heating of the Earth's surface during each season causes the oceans to experience differential heating as well. The differential heating of the oceans causes differences in sea surface temperatures at different latitudes and during each season. The equatorial latitudes of the Earth tend to have the greatest sea surface temperatures year-round because the sun's light hits that part of the Earth the most. The polar latitudes have the lowest sea surface temperature year-round because the sun's light hits that part of the Earth the least. The oceans are considered heat sink. That is, they absorb most of the sun's heat energy each day, week, month, and year. Despite this property of heat retention that the oceans have, this diagram shows that in the North American fall and winter months, September through February, there's a greater heat loss in the Northern Hemisphere oceans than in the spring and summer months, March through August. This heat differential change each season causes differences in evaporation and precipitation rates for each hemisphere of the Earth every year. If the sea surface temperatures of the oceans continue to rise, that differential will change as well, and this will affect the climate. Changes to Earth's orbit, eccentricity, its tilt, obliquity, and both orbit and tilt, precession, correlate with changes to weather patterns in the atmosphere and Earth's climate in discrete units of time. These phenomena occur every 20 to 100,000 years and are collectively called Lankovich cycles. For more information about these cycles and how they affected Earth's climate in the past, I encourage you to watch my video on glaciers, ice ages, and climate change in the Earth Science playlist on YouTube. If the Earth did not rotate on its axis, the winds and waters of the surface would circulate as in the diagram below. with the equator being the hottest point and the poles the coldest. In reality, we know that the Earth rotates on its axis once every 24 hours. This rotation causes the winds and surface waters of the oceans to rotate in a given direction in each hemisphere of the Earth. In the northern hemisphere, winds and waters are deflected to the right, or clockwise. In the southern hemisphere, winds and waters are deflected to the left, or counterclockwise. This phenomenon is termed the Coriolis Effect. In addition, the atmospheric winds in the troposphere also circulate in a series of patterns. These atmospheric cells create climactic belts at each major latitude of the globe. The atmosphere is divided into several cells of circulation due to the Coriolis effect. These cells occur at intervals of 30 degrees latitude. From the equator to 30 degrees north-south latitude are Hadley cells. Warm, moist air from the equator rises and produces plenty of rainfall and heat along these latitudes, generating the world's rainforest regions. From 30 to 60 degrees north and south latitude are Ferrel cells. The air from the subtropics dries and cools substantially as it approaches the greater latitudes, producing deserts and temperate zones. From 60 to 90 degrees north-south latitude are polar cells. The air is cold, it's farthest from the sun, and it gains moisture from the temperate zones and proximity to the oceans, creating intense blizzard and snowfall conditions in the polar regions. The surface winds of Earth, the trade winds, westerlies, and easterlies, play an important role in atmospheric and oceanic circulation. When these winds strengthen or weaken, storm systems and oceanic circulation patterns can change course. The trade winds originate along the equator and flow from east to west towards the subtropics. The region between the trade winds along the equator was referred to as the doldrums by sailors because the winds stopped altogether for months at a time. The westerlies originate in the subtropics and move from west to east, pushing storm systems north towards the temperate zones. The Earth's gyre systems originate from the connection between the trade winds and the westerlies, as do tropical storms and cyclones or hurricanes. The easterlies originate in the temperate zones and move toward the poles, moving from east to west. The connection between the westerlies and the easterlies can affect the polar jet stream, creating a polar front that fluctuates in strength each year, bringing cold weather much farther south or north in latitude than expected. This map of the world shows the climate belts in a spectrum of colors, in addition to the eastern and western boundary currents in each of the major gyre systems. Note that in Southern California, we're in the subtropical climactic region, the desert belt of the world. This means that we generally have little to no precipitation throughout the year, and fairly warm weather most days as well. For more information on gyre systems, check out my YouTube video on oceanic circulation in my oceanography playlist. The prevalence of extreme weather conditions, such as those caused by hurricanes or ENSO, the El Nino Southern Oscillation event, can be indicators of climate change. Hurricanes result from the change in pressure and temperature over the open ocean. They begin as a tropical storm or a tropical depression. During a tropical storm, the warm surface waters of the ocean create a low-pressure system. That low-pressure system meets with cold, dense, high-pressure storm clouds over the open ocean. This will generate a pressure differential, a vortex of high-speed wind that moves at 35 miles an hour or more, moves the storm clouds around the low-pressure center. These storm clouds will rotate due to the Coriolis effect and develop a hurricane. The center of the hurricane, the eye of the storm, is calm due to the low-pressure center there. Hurricanes have different levels of intensity. The faster the hurricane moves, the higher its rating on the Saffir-Simpson scale. A Category 1 hurricane is a tropical storm. It can build up to a devastating Category 5, depending on the pressure differential, speed of the winds, and energy as the storm moves across the ocean. Most hurricanes lose energy as they make landfall. However, as the oceans continue to warm along with the land, This trend has changed in the past few decades. Some of the most devastating hurricanes to make landfall in the United States recently include Hurricane Katrina in 2005, Hurricane Irene in 2011, Hurricane Sandy in 2012, Hurricane Matthew in 2016, and Irma in 2017. Coastal flooding destroyed millions of dollars worth of homes and businesses due to these events, and more are on the horizon with changing climate. Another source of coastal flooding is ENSO, the El Nino Southern Oscillation event, a phenomenon that affects the west coast of the Americas every 5 to 10 years approximately. There are two phases to ENSO, El Nino and La Nina. El Nino is named after the Christ child because these storms occur around Christmas time each year, as initially observed by fishermen off the coast of Peru. During an El Nino phase, the trade winds will weaken. The pool of warm surface water in the Pacific that's usually confined to the east coast of Asia and Oceania will spread out. With this movement of warm surface water across the Pacific, a low-pressure system will develop. This will bring intense rainfall to the west coast of the Americas and drought to Asia and Oceania. During La Nina, the trade winds will strengthen. This causes the warm surface water to remain even more confined to the east coast of Asia and Oceania. This means that the monsoon season will strengthen in Asia and Oceania while drought will strengthen along the west coast of the Americas. It's uncertain whether ENSO events are tied to climate change. However, warming surface waters will increase the intensity of these events in the foreseeable future. This concludes this week's lecture on weather and climate. Feel free to check out my other videos on YouTube and Earth Science and Geology, and thanks for watching.